So in the last video we had the coproduct topology. In this video we're going to have the product topology. Okay, so again let Y and Z be topological spaces. And we're going to introduce a topology on Y cross Z. Okay. So let's suppose X is a point, say Y comma Z, lying in Y cross Z. And U is some subset of Y cross Z. So a box around X and a set of the form V cross W, B maybe, V is V cross W, with Y is in V, which is a subset of Y, Z is in W, which is a subset of Z, where V is open in Y and W is open in Z. Okay, so that's what we mean by a box. And we say that U is open if every point in U there is a box V cross W with X in V cross W, and that's contained in U. Okay, so every point of U can be surrounded by a box which is going to be contained within U. So a picture kind of like this. This would be a picture sort of with Y and Z both being the real line, say, so Y cross Z is the plane, and then here's our U, and then maybe we've got a point X here, and we're supposed to be able to surround that point by a box. The box would be like this. So here's our V here, here's our W here. That's this is V cross W. It's a box around X that's contained within U. And, if every point in U has such a box, then we're saying that U is open. So then the so the key claim's got to be that this defines a topology on Y cross Z, which we're going to call the product topology. Okay, so we want to prove that the product topology is a genuine topology, but before we do that, we're going to have a couple of lemmas. First one, if V is open in Y and W is open in Z, then V cross W is open in Y cross Z. And the proof is very straightforward. Suppose X is in V cross W. We need to provide a box B if X in B and B contained in V cross W. But we just take B to be equal to V cross W. Okay, there's nothing really to do. The second lemma is going to be nothing actually very specifically to do with the product topology, but just a kind of basic thing about how topological spaces work. So now here let X be a topological space. and U is just some subset of X, and we want to prove that U is open. And suppose that for all X in U, there exists an open set, let's call it NX, with X has to be an element of NX, and NX has to be contained in U. So if we've got all these NXs, then I'm going to claim that U is open. And for the proof, well, I'm going to put U upper star as the union over X in X. So over X in U of NX, the union of all these sets. Okay. So that's a union of open sets, therefore it's open. So it's enough to show that U is the same as U star. But then each NX is contained in U. And it follows that the union of all the NXs is also contained in U. But then as X lies in NX, for all X in U, we have U upper star is contains U. Okay? We've got any point in U, well then it's contained in NX. If you've got any point X in U, then it's contained in NX, and so it's contained in U upper star. So that proves that U is contained in U upper star. So now we've got it both ways around. U star is contained in U and vice versa. So those sets are the same, and so that means that U is actually open. So now let's prove that the product topology really is a topology. So proof, okay. Well, firstly, the empty set is the empty set cross the empty set is open, and Y cross Z, that's Y cross Z. It's also open. These are both just because boxes are open. Okay, so that was a lemma we proved a second ago. If you take a box like this, then that'll be open. Okay, so let's suppose we've got a family of open subsets of Y cross Z. And let's put U upper star as the union over I of UI. So we need to prove that that's open. Okay, so suppose X is in U upper star, so we need to now provide a box around X that's contained in U upper star. But what does it mean to say that X is in U upper star? That just means that X, that means that there exists I. Right, to say that X lies in the union just means that X lies in one of the individual sets UI. As UI is open, that means there is a box, V cross W, so it's got to be a box around V cross W that's contained within UI, but of course UI is a subset of U upper star, so that means that this box is actually contained in U upper star as required. Okay, so that proves that U upper star is open. Now we need to show that suppose that we've got some finite list of open sets and we need to check that their intersection is open. Okay, so right, U hash is U1 intersect UN. So let's suppose that X lies in this intersection, which just means the same as saying that X is in UI for each I. Okay. But UI is open, so we have a box. So X lying in, say, VI cross WI contained in UI. And so now we can put V hash is V1 intersect up to Vn, W hash is W1 intersection of all the WIs. So V hash is open in Y, right? That's because this was supposed to be a box, which means that VI is open in Y and WI is open in Z. And so V hash is the intersection of finitely many open sets in the topological space Y. So that's again open in Y. W hash is open in Z. And X lies in V hash cross intersect W hash, which is contained in U hash as required, right? Because X lies in all the VI. X is Y comma Z, where Y lies in each of the VIs, and therefore it lies in the V hash. Z lies in each of the WIs, so it lies in W hash. So X is in V hash intersect W hash. But then because VI intersect WI is contained in UI, we see that this intersection is contained in U hash as required. Okay, so that proves that we really do have a topology. So now we want to know some stuff about continuous maps to or from this product set with this product topology. Firstly, we're going to define maps, projection maps, P and Q. So P sends YZ just to Y, and Q sends the pair YZ just to Z. And you want to claim that these are continuous. And so let's suppose that V is some open subset of Y. Well, then what is P inverse V? That's the set of pairs YZ with Y in V, because Y is just it's the same pairs where P of YZ lies in V, but P of YZ is just Y. And that's just the same as V cross Z. And that's a box. So that means P is continuous, and similarly Q. Now we want to consider something about a bit more general about continuous maps, but we're going to revert for a minute to the case just of sets. So now let's just let Y and Z be sets. And then T another set. Good. So go back to here. So then any map F from T to Y cross Z has the form F of T is G of T, H of T. For some maps G from G, if we want, we can express that as P composed with F from T to Y, and H, which is just Q composed with F from T to Z. So F of T has to be a pair with one element in Y and the next element in Z. So the first one we can call GT, the second one we can call HT, and then P composed with F is sending T to GT, Q composed with F is sending T to HT, so G is P composed with F and Q is so this is how you get all your maps from T to Y cross Z. And so we see that sets T, Y cross Z, it's a set of maps from T to Y cross Z. That's in one-to-one correspondence with the product sets TY cross sets TZ. And with a single function F from T to Y cross Z corresponding to the pair G, H. So kind of the point about the product topology is that F is going to be continuous if and only if G and H are both continuous. Okay, so let's just write that again. Suppose you've got a map F from T to Y cross Z, given as before, F of T is G of T H T. Then F is continuous if and only if both G from T to Y and H from T to Z are continuous. There's the proof. Well, firstly, let's do the easy half. Suppose F is continuous as the maps, the projection maps P and Q are continuous. So are the composites G, which is P composed with F, and H, which is Q composed with F. So conversely, let's suppose that G and H are both continuous. Okay, so let's suppose we've got some open set U here. So let's suppose that T lies in the preimage of U. We're supposed to be proving that the preimage of U is open. Okay, so what does that mean? That means f of T lies in U. And remember, of course, that's the same as the pair GTHT lies in U. This U is a subset of U is a subset of Y cross Z, and we're saying it's open. In other words, it's open in the product topology. So f of T is a point of U, and so by the definition of the product topology, we've got a box V cross W which contains f of T and is contained in U. So that means that GT, so for FT lying in V cross W, that means that GT is in V and HT is in W. So that means that T is in G inverse V intersect H inverse W. So let's call this set NT. It's open because G and H are continuous. Okay, G is continuous and V is open in Y, so G inverse V is open in Y. And W is open in Z, and H is continuous, so H inverse W is open in T. And so this is the intersection of two open sets of T, and so it's open. And that's what we're going to call NT. Yeah. And also, if we've got some T prime in MT, then that means that G of T prime is in V and H of T prime is in W, right? Because T prime is in G inverse V intersect H inverse W, so T prime is in G inverse V, so G of T prime is in V, and similarly H T prime is in W, and therefore F of T prime is in V cross W, which is contained in U, and that means that this means that T prime is in F inverse U. So that means T is in NT, which is contained in F inverse U, and so by the lemma that we had a minute ago, we wanted to prove that this F inverse U is open. We've shown that for every point T lying in F inverse U, we've got an open set NT that contains T and is contained in F inverse U. So F inverse U is open by a lemma that we had a minute ago. So this completes our characterization of the continuous maps into Y cross Z, which can be expressed in the general language of category theory as saying that Y cross Z is a product of Y and Z in the general sense of category theory, and that's kind of why it's called this product topology.